This video looks at time of flight mass spectrometry, particularly how this technique works and the calculations that you might be expected to do and the questions you might need to answer. And this is specific to AQA A Level chemistry syllabus. So before we start looking at mass spectrometry, it's a good idea to remind ourselves what we mean by the word relative mass when we're talking about atoms. So if we tried to measure atoms in actual mass units like grams, it's going to be very time consuming in our calculations because, as we can see here, one atom, a single atom of carbon-12, weighs 1.99 times 10 to the minus 23 grams. So it would be very awkward if we had to keep doing this for every single atom when we're working out things, especially for mole calculations, etc. So what we do instead is we have this atomic mass unit, and the atomic mass unit is basically related to carbon-12 isotope, and we'll actually look at the end of the video why we use carbon-12 in particular, but everything else is relative to this atom. But this atom doesn't have a mass of 1, right? It has a mass of 12, that's why we call it carbon-12. So what we're saying is we're going to measure them all relative to that. And so, for example, if I took magnesium-24, that isotope has twice the mass of a carbon-12 atom. So relative simply means where one proton has a mass of 1, one neutron has a mass of 1, and we work out all our atoms. Now, in the past in GCSE, you might have referred to mass number. So, for example, if I look at these three isotopes, we've got magnesium-24, 25, and 26. So they have different mass numbers, and they've got obviously the same number of protons. That's why they're isotopes of magnesium. But technically, so mass number is simply I look at an atom and I add up the protons and neutrons. But we could also refer to that same number as relative isotopic mass. So isotopic mass is basically what we're saying, it's the relative mass compared to 1/12 of the mass of a carbon-12 atom. It seems a bit clunky, but if you think about it, you take a carbon-12, it weighs 12 units, you divide it by 12, that gives you 1. We're just saying where the scale comes from. So remember that definition. That second part is the bit about it being relative. Now, isotopic mass is the same as mass number, essentially, and it's always a whole number. But on the periodic table, what we have is not isotopic mass, what we have is relative atomic mass. So the relative atomic mass of magnesium on your A-level periodic table is 24.3. And that is because that is a weighted mean, i.e. an average mass of an atom relative to 1/12 of the mass of a carbon-12. So the second part of that definition is exactly the same. Very important to remember it. Other things that people forget in this definition is it is an average or a mean. The weighted part means that we're taking into account the fact that not all the different isotopes, so magnesium 24, 25, 26, have the same abundance. And that's what we'll look at later with our calculations of relative atomic mass. And the things that people forget is this word atom. Oh, it's really important to remember that both of these are the mass of an atom, because otherwise what people do is they say something like it's the mass of an element. It doesn't really make sense to say it's the mass of an element. What do you mean? Like the mass of magnesium? No, the mass of a magnesium atom is what we're weighing here. Okay, so mass spectrometry is how we find out those masses. So mass spectrometry is a very sensitive technique which can measure the mass of individual particles, sometimes to a very large number of decimal places, which we will look at the end of the video. And in the main uses that we need to know, it's used to find the abundance of these isotopes, so relative amounts of these different masses of atoms, and it is used to find the molecular mass of molecules. So that is usually used in organic chemistry when we're trying to find the identity of an alkane or an ester or something like that. So I'm not going to focus on that in this video because that will come under our organic chemistry. There are many other uses of mass spectrometry, as you might expect. What you learn at A level isn't everything, right? So there are lots of other ways that it is used. So there are also lots of different types of mass spectrometer, but we are going to look at something called time of flight. So let's just do an overview first, and then we'll go into a bit of detail on the bits that you need to know more about. So it's like a very long tube, longer than this diagram suggests. At one end, we're going to vaporize the sample. So what that means is we want everything to be spread out so that the particles are spread out. So if it is something like magnesium or iron, like a metal, we're going to need to turn that into a gas first. You can't just stick a lump of iron into a mass spec. So we inject it into the end of the sample. Now, atoms are almost impossible to detect, okay, because they don't do anything. You know, if an atom hits you, you didn't notice, okay? So what we need to do is ionize. Every type of mass spec, whether it's time of flight or any other type, has an ionization step right at the beginning. And although you may have learned about ions being either positive or negative, either losing or gaining electrons, in the purposes of mass spec, ionization means to form a positive ion always. Then what happens? Well, there's no point just leaving them at the end of that tube. So what happens next is they are accelerated so that they're all moving in the same direction. And we just do this because they now have a charge. They can be attracted towards the negative side and repelled away from a positive plate. They go through the holes and they go into the middle part of the mass spec, which is called a drift tube or the drift region. So this is a very long tube, usually around 1 or 2 meters in length, which is long for a particle. One thing I also didn't mention is that inside of this is a vacuum. So we can't have air particles inside the mass spec because air particles actually would really slow these particles down because they'd constantly be bumping into them and changing direction. And the speed of the particles is actually how we find out their different masses. So they all have the same energy because they're all accelerated based on their charge due to like a particular amount of voltage that is applied. They have the same energy, but they don't have the same mass. And as we'll look at the calculations, what that means is that lighter particles travel faster and they will reach the end of the mass spec and reach the detector first. Lighter, not smaller. Please don't talk about the size, especially if you're talking about atoms. They're all going to be the same size. They've all got the same number of electrons, etc. If they're isotopes of the same element. So it's not about size, it's about mass. Okay, so let's look in more detail about some of these steps that you need to know more about. One of them in particular is ionization. There are 2 different ways that we can form these positive ions, and it depends usually on the type of sample that we're looking at. So one of the most common forms, especially for isotopic abundance, is electron impact. So this is used for elements, so i.e. magnesium or iron or neon or whatever. It is also used for low molecular mass compounds or small molecules like Cl2 or Br2. Okay, so how do we get the atoms to become ions? And this circle here can represent an atom or a small molecule. Okay, so it's just a particle. So first of all, what we do is we use something very exciting, which is called an electron gun. All that is a piece of metal, really, that you just heat, and it turns out that electrons are given off the surface of many pieces of metal when you heat them up. So we're firing electrons, and they're quite high speed because they're going through a vacuum and there's nothing in the way of them. So these electrons are going to fire at this particle. Now you might be thinking, hang on, I thought we were making a positive charge. Why are we firing electrons at it? Electrons have a negative charge. Well, the thing is that whether that is an atom or a molecule, it has electrons around the outside. So the first thing these high-speed electrons are going to hit is the electrons that are on the outer shells of that atom or molecule. Electrons will repel, and so the one electron will hit that atom. Let's call it an atom for now. That electron will bounce off and at the same time will repel one of the other electrons because of its high speed and push another electron out of the outer shell. And you get a positive charge, a single positive charge. Now you need to be able to write an equation for this process. So let's say that it's going to be just X. Okay, we're going to call it element X. We have to put state symbols in these types of equation quite often. It is always going to be a gas state. You can't have particles all stuck together in a solid or a liquid. You need them separate, otherwise you can't weigh their individual masses. So we have our X, and technically what we're doing is firing one electron. I know in my diagram there's lots of electrons there, but you only need one electron to hit my atom to knock off another electron. So that is on the left-hand side. It kicks out one of the electrons from the X outer shell, so you end up with X with a positive charge. That is obviously still in a gas state, and basically what you've got left over is the original electron that you fired in, plus another electron that you just knocked out of the outer shell. So this is quite an unusual way where we wouldn't normally write electrons on both sides. If it was ionization energy, which you're also studying at the same time in this topic of atomic structure, just be careful, because for ionization energy, we just have one electron on the right-hand side, and we just say we don't put the one on the left. Okay, so we're just removing it, usually by other methods. So this is very good technique. It's very simple. We would use it for, like I said, samples of an element where we just want to weigh the abundance of isotopes. But if I want to use it in organic chemistry, where I want to do a larger molecule, and I want to know the molecular mass of a really big molecule, then the problem with this technique is that it would essentially cause these larger molecules to break up. So if you think about organic chemistry, it's mostly based on carbon. Carbon is forming bonds with all of its electrons. And so if you knock out an electron, the chances are that that electron was actually part of a bond, and that bond is likely to break. So what we mean by fragmentation is that those bonds break, the molecule breaks up. Now, sometimes that's useful because I can actually find out more about the molecule, like the order of the atoms. But often we want something that is called a softer ionization technique. And by that we mean something where a larger molecule doesn't break into different fragments. So we use something called electrospray ionization. This is a little bit harder to explain, so I'm just going to focus really on the main bits that you need to know. A thin needle, so really, really thin, okay? You're firing it through. Now beforehand, your molecules have been dissolved in a solvent. They will say it's a volatile solvent. That just means it evaporates easily. So not something like water, something like a organic solvent, like nail polish remover type stuff. Okay, it evaporates real quickly. You have a really dilute solution, and you put it through the needle, and what that does is pushes these little tiny droplets out, just like a spray bottle does. Okay, so it pushes it through and they all spread out. At the same time, we are applying a voltage. So what this is showing is individual little droplets, and each of the droplets is probably going to contain like a single molecule of what I'm interested in. We apply a voltage, and the voltage causes the particle not to do anything in terms of electrons. What it's going to do is gain a hydrogen ion. This is pretty common in chemistry. It's a pretty common way that things form charges, especially larger organic molecules. So they gain H+. So we could actually show this in an equation as well. So this time what we would say is X plus H plus goes to X H plus. So that's what's happening in this type of ionization. And then we actually need to get rid of the solvent because we don't want the mass of the solvent as part of everything that's going on. So all we need to do there is just heat it. The solvent will evaporate away and will leave behind the ions, which can then get accelerated and move to the detector. So in both of these processes, the upshot, what we're making is something with a positive charge that is accelerated and moves to the detector. And then what happens next? We accelerate them. They all have the same kinetic energy, and that's just related to the voltage used, and we'll look at why kinetic energy is important. It means that, as we said before, the velocity, the speed of each of these ions depends on their mass. And because they are all traveling the same distance, but at different speeds, they will take a different amount of time, which is where time of flight comes into it, to reach the end. And at the end, they get detected. How do we detect them? Well, they are ions. They're going to hit a metal plate. They're going to gain an electron from that metal, and this is going to cause electrons to move through it and generate a current. And the current is directly proportional to how many ions are hitting it at that time. That's a really important exam point that is often asked in questions. Okay, now we're going to concentrate the rest of this on the calculations involved for time of flight. So there are two equations that we tend to need to use for time of flight calculations. We've got kinetic energy is equal to a half mass times velocity, which is obviously also written as Ke equals 1/2 mv squared. All right, so let's talk units because units are very important for getting this right. Kinetic energy is going to be in joules. The mass of atoms, so in chemistry we're used to dealing with mass in grams often. When we do mole calculations, this is more of a physics equation than a chemistry equation, so we're going to be doing our mass in kilograms, which is the standard SI unit for mass. And then the standard unit for velocity or speed is meters per second, which is often written like that. Okay, and then the other types of calculations. So this means that if we know the mass of an atom and we know its kinetic energy, we can work out its velocity. And of course, we can rearrange to find any one of these. The other equation that we're going to need is to remember our GCSE physics, that velocity is the distance over time. Don't at me about the difference between distance and displacement. It really doesn't matter in this example. You can call it speed if you don't want to call it velocity. That's in meters per second, which means our distance is in meters and our time is in seconds. Time is normally very, very short. So this is basically the time of flight that we're talking about, the time it takes to move through the drift region and to the detector. And then this is our distance, which is often called the length of the tube or the length of the flight tube. So that's something to look for. You think, okay, I've got to find distance. Usually we're wanting to find time or distance, which means we've got to first find the velocity and then we've got to find either the distance or the time based on that. First of all, though, the problem here, the first thing that we have that makes this calculation a little tricky is that the mass of atoms is suddenly in kilograms. And as we said at the beginning of the video, that's not how we measure atoms. So here's an example where we want to calculate the mass, in this case it will be in kilograms, of a single barium ion, which has a relative mass of 138. So remember that relative is also related to the mass of 1 mole. So what it tells me is that 1 mole of barium 138 has a mass of 138 grams. Because remember, these atomic masses, relative atomic masses, are in grams per mole. Okay, also, this is an ion, not atoms, but remember that electrons really have completely negligible mass. So the mass of a Ba plus, or indeed a Ba2 plus ion, is going to be exactly the same as the atom. So we can ignore the fact that it has a charge when we're doing this calculation. Then we have our Avogadro's constant. So what that tells us is the number of atoms in 1 mole. So 1 mole is equal to 6.022 times 10 to the 23 atoms or ions. So if I want to know the mass of an individual atom or ion, I would take the mass of 1 mole and divide it by the number of particles in a mole. And I get 2.29 times 10 to the minus 22, but that's in grams. And if I'm using this for a time of flight calculation and I'm using it in the kinetic energy, I need to put it into kilograms. So I'm just going to divide by 1,000 to get 2.29 times 10 to the minus 25 kilograms. Okay, so that's how we calculate the mass of ions, and we could go the other way. If we had the mass in kilograms, we could times it by 1,000, times it by Avogadro's number. That would get me the relative atomic mass. Okay, calculating the velocity of ions then, let's look at rearranging the kinetic energy equation. So the kinetic energy equation is K equals half mv squared. So we want to calculate velocity. So there are various different approaches to this that people would teach in different ways. I've got the mass in kilograms already, and I've got the energy in joules, and I'm trying to calculate V. I would recommend that we first do a little bit of rearranging, but not all of it. Okay, so there are two things you can do. You can either say, you can put all the numbers in, or you can rearrange it to find V squared. So V squared, if I times both sides by 2, is 2ke over m. Now, you can just go straight to V equals square root of that, right? Because that's what you want to find in this question. I would say it is basically down to your maths competence and how often you make silly mistakes when putting things in the calculator. I would also recommend in all of these questions a big use of the answer button on your calculator to not have to keep typing these numbers in over and over again. So there's a bit of a balance. I don't want to have to keep writing stuff down. Every time I write stuff down, I might make a mistake, but every time I don't write stuff down, I don't get any working marks. So since V squared is usually a working mark, let's calculate V squared. So it's going to be 2 times the kinetic energy, 9.25 times 10 to the minus 17, over the mass, 6.64 times 10 to the minus 26. Now, again, I'm going to talk about calculator technique here, because I see this done wrong a lot. Okay, and this is what's happening. It's not rearranging wrong, it is typing it badly into the calculator. So you have 2 lots of standard form in this calculation. I'm going to recommend that you use the button on your calculator, you know, with the little circles, little fraction button. Make sure that you've got stuff on top and bottom. I'm also going to recommend that you use the button that says times 10 to the power. And I'm sorry if this is really easy to you, fine. But if this is the mistakes you're making, because when you type individually times 10 to the power, and you do all of that separately, your calculator doesn't understand that this is all one number and that this is all one number. Okay, and what it will start to do is ignore the standard form and start doing the 10 to the minus 26. So what I mean is we divide it by 6.64 and then we times the whole answer by 10 to the minus 26. So the other way to catch this is that v squared is going to be massive, really, really big. Okay, so v squared is a big number. When you square root it, it is still going to be a big number. So the answer to this in total, you can pause it and have a go yourself and make sure that your calculator technique is sound. You should get a velocity of 52780 meters per second. So that is like 52,000, nearly 53,000 meters per second. That is pretty common. Okay, so we're talking tens, hundreds of thousands of meters per second. So if your answer is like 10 to the minus anything, clearly you have not done the right velocity. Okay. If your answer is in the millions of meters per second, then it means that perhaps you forgot to square root. So these are useful things to think about. Let's do a full calculation. So let's look at a full example of a time of flight calculation, which could be worth maybe 5 or 6 marks. So we have the ion traveling through the mass spectrometer. We are trying to find the length of the flight tube. So we're given the relative mass of the ion, we're given the kinetic energy, and we are given the time it takes. So there are actually 3 different things we really need to do here. We need to get mass in kilograms. So from the 86, we need to get the actual mass of the single ion. We then need to find the velocity using k equals half mv squared, and then we need to find the distance, which is our length of flight tube. So mass in kilograms, as we did before, we've got, first of all, we can do mass in grams, which is our mass of 1 mole, 86 grams, over the number of ions in a mole, 6.02. In some of these calculations, it's been 6.02, and some it's been 6.022. Just use the one that you're given. And so the mass in grams is 1.429 times 10 to the minus 22. 4 sig figs is perfectly adequate, but actually I'm just using this answer in my calculator the whole time. Again, with the Avogadro's number, be careful that you are making sure that 10 to the 23 is definitely dividing that number and not being tacked onto the end of your calculation. So the mass should be really small, and then when I get mass in kilograms, it's going to be even smaller. Divide by 1,000, 1.429 times 10 to the minus 25. Now I would do that and have it in my calculator. It may have a load of extra decimal places, because I can just use the answer button in the next step. So if I want to find, I'm going to calculate v squared. Again, I'm just showing this technique because it's often a mark in the mark scheme, rather than, you don't get any extra sort of bonus marks for literally throwing every single part of this calculation into one calculation. And what's more likely to happen is you type something wrong and get something wrong. So I'm going to calculate v squared as 2ke over m, and I am going to put in my kinetic energy, 1.921 10 to the minus 15, my mass 1.429 times 10 to the minus 25, but really what I'm doing here is just pressing answer on the calculator. I get v squared as a very large number, right? So it should be like 10 to the 10 times 10 to the 10, and then I'm going to square root it to get v, and again I'm just doing square root answer. I'm not typing these in all the time, and I'm just leaving lots of significant figures in here at the moment. And then I'm going to rearrange the v equals d over t. I want distance because I want the length of the flight tube. So I want meters, so distance is equal to velocity times time. So I get my distance 1639, doesn't matter if you round this up a little bit, times 1.09 times 10 to the minus 5, and I get a distance of 1.79 meters to 3 sig figs. Now, obviously be careful of your rounding. I think it was actually 1.78 something. There may well be a range, so if you did round up in the middle, that's fine. Don't round to less than 3 significant figures, because if you do that, you can't go less than and then suddenly add on another significant figure at the end of the calculation. The length of flight tubes is always roughly around this size, okay? So it's somewhere between 1 and 2 meters usually. I'm not expecting it to be, so if you've got like 1,000 meters, you've done something wrong somewhere, have a little look and see if your answer makes sense and is similar to what you normally have. Okay, other little questions we can have about mass spec. It's not just time of flight calculations, there are of course relative atomic mass. So I just want to spend the rest of this video looking at those examples, which is relevant to all exam boards, not just AQA. So the data that we get from a mass spectrum has 2 axes. And so it tells us 2 different things. It tells us the mass of each isotope and the relative abundance of each isotope on. That is the height of the peaks. And the mass is on the bottom. But if you notice at the bottom, what it actually says is mass charge ratio, or it may say MZ, or it may say M/E. It really does depend on the example that you're looking at. So what that means is, if we go back to ionisation, in ionisation, particularly, we're most likely to be using electron impact for this kind of spectrum. And if we're doing that, then what we end up doing is we take our atoms and we give them a +1 charge. Now, if they don't get ionised, that's a very good question. Sometimes people say, well, what happens if they miss it? They don't get an electron knocked off. Well, if they don't get an electron knocked off, they don't get accelerated to the end of the detector, so we don't detect them. And we wouldn't detect them even if they did drift over to the end of the detector, because they haven't got a charge, so they're not going to make a current. So anything that doesn't get a charge doesn't make it into our mass spectrum. It doesn't matter, because all we want is a relative amounts of each isotope. And because there's like millions and billions of atoms in there, we're still going to get what we need to find out. So if we take what we mean by mass charge ratio, the kinetic energy that it's given depends on the charge that it has. Or if you're looking at other types of mass spectrometer, the deflection depends on the charge and the mass. So in this case, if the charge is 1, then the mass charge ratio is 20 divided by 1. So if the atom lost 2 electrons instead of 1, it would appear at a different point on this axis, because it would have a mass charge ratio of 10, even though the relative mass of the atom is 20. So, doesn't matter. 2 reasons it doesn't matter. One is, statistically, a very, very small number of these atoms will end up with a 2+ charge. If they do, they will be in a region of the spectrum that I'm not even looking at. Because if I put neon in a mass spectrum, then I'm looking for neon. And if I want to know the isotopic abundances of this sample, I'm not going to be looking down at 10. And if I do, it would be such a tiny, tiny peak, I probably wouldn't even see it. I'm only mentioning it because of the occasional random little question. If it says something that is half the mass charge ratio of what you expect, it's not because it's got half the mass. Usually it's because it's got double the charge. Okay, calculating relative atomic mass. Here's a really mean example with 5 different isotopes of calcium and all of their percentage abundances. So all you've got to do, it doesn't really matter how many isotopes you have, is you've got to keep adding it all up. So relative atomic mass can be also written as AR, is going to be 40 times 96.94 plus 42 times 0.65 plus 43 times 0.14, oh, it's getting tight, plus 44 times 2.09 plus, I knew I wouldn't make it, 48 times 0.18. Add all of that up and divide by 100 and you get an answer of 40.1152. Then have a look at the question to decide on the amount of rounding necessary. It may say 3 sig figs, in which case 40.1. If it says 2 decimal places, remember to be careful of your rounding. In that case, that would be 40.12. Don't round too much. If you're not given any information, then just chuck it all in. Simply because the whole idea of this is that we are potentially going more accurate than what's on your periodic table. So I don't want to just write 40.1 necessarily unless I'm told to do 1 dp or 3 sig figs. Okay, a little thing to check is that the data that we get from a mass spectrum is abundance and the mass charge ratio, as we've said. Don't always 100% assume that abundance is a percentage. So this abundance isn't. It's just relative numbers. It could be related to the current. So it could say something like, the current detected instead. Or it could say something like arbitrary units. So the whole point is that these are just ratios. They don't have to be percentages. So in this situation, they're usually given as percentages, but they may be given as absolute values. And you may have to measure them off the spectrum. So it's just the height of the peak. If you need to do that, just make sure that you use a ruler to get the relative numbers. And it doesn't matter whether you use millimeters or whatever to measure it, because obviously as long as you use the same unit each time, it's the relative numbers. So let's see how you would use this spectrum to calculate relative atomic mass. It's still the same equation, mass times abundance, add them all up, divide by total abundance. So the only difference here is I'm not dividing it by 100 because these three numbers don't add up to 100. If I add them up, the total is 73.3. Other than that, it's the same equation. So 60.1 times 84 is the mass on the x-axis there, plus 10.5, watch out for little extra multiplies that come on the middle here instead of plus, times 85, plus 2.7 times 87, and this time instead of being all over 100, it's all over 73.3, and I get my answer as 84.3. I've done that to 3 sig figs. I know that it's correct. I'm expecting my answer to be closest to 84, right? Because there's only very small amounts of 85 and 87. If you get a number that is not between 84 and 87, hopefully you will realize that is wrong. One thing I also want to point out is this isn't the number on the periodic table for this particular element, which is krypton. So on my periodic table, krypton is 83.8. But that's okay because it says this sample of krypton. It's not saying naturally occurring. It could be krypton from another place that has slightly different percentages of different isotopes. And that's pretty common because they don't want to just lead you to the same answer that you've already got in front of you. Final thing, just to look at high resolution mass spec. What is that all about? So mass spectrometers can be very, very sensitive instruments indeed. And a high-res mass spec can actually identify molecules using their exact MR values. So sometimes we use this kind of thing to detect like just a particular molecule. So for example, in the airport, when they're scanning your stuff and they want to know if you've got a particular explosive or something weird or some drugs or something in your cosmetics, they are often using this type of instrument. So let's take these three examples of molecules. So if I add up the molecular masses just using the periodic table, on the periodic table that we use, carbon is 12 and hydrogen is 1 and oxygen is 16, and all three of these molecules have a mass of 44. However, in real life, there are always more decimal places, right? So in real life, if I have these three elements to 4 decimal places, these are the actual relative atomic masses based on the isotopes present. So notice carbon is still 12.0000. That's why carbon is used as our reference point for masses, because it has a very small number of other isotopes, and so when we say the relative atomic mass of carbon is 12, like, it is 12. But what I can do is use these masses and the molecular formula to add up, and what we will see is that these three molecules, when I look at them to 4 decimal places, do have different MR values. So I could tell the difference between CO2 and propane and this weird little ethanol molecule as well. One thing to notice about this is that isomers are still going to have the same mass, exact same MR value, because they have exactly the same molecular formula. So these two examples here are still C2H4O. So it does not help distinguish between isomers. I could potentially use fragmentation, so the point where they break up, to distinguish between these isomers, but that's something that you would look at in organic chemistry separately.